Hi, I'm Melissa Ann Pfeffer. I'm an atmospheric volcanologist who works at the Icelandic Met Office, and in this video we're going to go over the software that we use for collecting the traverse DOAS data and for processing the traverse DOAS data. So the Icelandic Met Office is a partner in the NOVAC project. This is an international project of volcano observatories and scientists who support volcano observatories for measuring SO2 flux from volcanoes. And this project has developed a lot of both instrumental techniques and software to help us in the collection and the processing of data. So right now we're going to be talking about the traverse DOAS measurements. We were out in the field earlier this month. There's that footage that you've probably already seen. And now I'm going to show you some more of the details of the software that we use. If you want to download the software for yourself, you just need to do a Google search for NOVAC, and then the software for the traverses is called Mobile DOAS. And then you would just download the newest release of this software. So what I'm going to show you now is how, when we've gotten back from the field, how we calculate the flux of the SO2 from the eruption from the traverse that we have just made. So what I'm going to do now is open up one of my most recent files that I collected. So analysis, calculate flux from file, open log file. Then the last time that I was out making these measurements was the 26th of August. So then I go into, so here's the folder for the 26th of August. I choose one of the traverses. We made 5 traverses, 6 traverses the last time I was out in the field. Then we choose the log file. So this is what a good traverse looks like. What you can see here is that there is a baseline around 0 before there's a large peak, and then we come down, and then we have another baseline back to 0. So this is showing us the red line is showing us the series of measurements that we made from when we started to when we ended the acquisition. So what we do is, when we look at this, we look and we try to see, okay, where did the plume start? We move this little cursor over to where it looks like to us the plume has started. So this is where it looks to me, where the baseline is going above 0 and starting to rise. This is where we're at the fringes of the plume. Then we move the other cursor also to the other end of the plume. So it looks like this was a plume that had a very strong concentration right in the center, but also very low concentrations of SO2 going very, very broad. This particular traverse, I'm going to go to View, and then I'm going to go to the Show the Route Map. And here you can see that it was actually quite a long, broad plume on this day when we were making the measurements. We were driving, for the Icelandic people, we were driving all the way from Hafnarfjörður, all the way past Grindavik, almost all the way to Njarðvík. And you can see that there's the red colors show where there's a lot of SO2, and then the blue is where we're getting closer to 0. So I close this again. Now, so we've moved the cursors over to these two. And now what we do is we have to put in the wind speed and the wind direction. And so what I do is I collaborate with a meteorologist. And every time I make a traverse, I send her the details of the road that I was driving, the time where I had the peak in the SO2. So I would, for this one, I would tell her the time was 14. And then she gives me 2 end members of wind speed and 2 end members of wind direction. So for every single traverse, I make 4 calculations. So now we're going over to another computer where we have an Excel spreadsheet where we're keeping track of all of the traverses that we make. So here we have the traverses. Then we have the file name. So this is the name that's produced by the Mobile DOAS software. Then the time that the SO2 is at its peak. So in that example that we were just looking at, it would be 14 o'clock. The location, so where we drove or walked in order to do this traverse. Then this is important, the wind direction from the software. So I'm going to go down to this measurement that we're working on right now, which is right here. This is the 26th of August at 2 o'clock. We drove on Reykjanesbraut, and the wind direction from the software. The Mobile DOAS software determines the wind direction from the eruption to where you made the measurement using 2 different techniques. It depends on the shape of the plume that you're measuring. If you have a very nice steep plume where you clearly have a very high point, you would choose the maximum SO2 to calculate the wind direction. But if you have a plume with more peaks and it's very broad, then you would choose the center point. So this wind direction from the software, this is very important for the meteorologist. So the meteorologist uses this to help pinpoint which height in the atmosphere they should be retrieving the wind speed and the wind direction from. So the meteorologist is using different sources of information in order to provide two end members of wind speed and wind direction. So one of the tools that we use are balloon launches. And I remember that I talked about this when we were out in the field. So we have an airport very close to the eruption. So twice a day or 4 times a day, depending on the time of the year, we have a balloon launch which provides us with different wind parameters at different elevations. The other main tool that we can use are the ground stations, which show the wind speed and the wind direction at 10 meters height. And we also have the forecast model. The forecast model also provides the information at different elevations. So the wind direction from the software is very helpful for determining exactly which height we should be using. So during the film from Talvan, he'll probably be talking about the plume height retrievals, but we have a time series of plume height retrievals from the webcams throughout the course of the eruption. And very often throughout the eruption, it's around 1.5 kilometers height or 850 hectopascals, but there is quite a bit of variance around this. And so by looking at the wind direction from the software, it really helps the meteorologist to determine either which model level or which balloon level is most suitable for the particular traverse that we just made. So then we put into the spreadsheet 2 end members of wind speed. So on the 26th of August, it was either 6 meters per second or 8 meters per second. Those are the 2 end members that were considered most characteristic of this measurement. And then 2 wind directions. So we have the 2 end members are 175 and 195. Now we're back over on the machine that has the mobile DOAS software. Now we have opened this traverse that we're calculating the flux. We've moved the cursors to say the beginning and the end point of the plume. Now we put in the wind speed 6 and the wind direction 175. And while we have this one open, you can see that in this traverse, the maximum center was 179.9 and the average center was 178.6. So I put 179 as the value for the meteorologist to look at. So we have the wind speed of 6, the wind direction of 175, and I'm processing all my data in the units of kilograms per second. So I choose kilograms per second, and this traverse gives a flux of 153 kilograms per second. So we are going to repeat this calculation 4 times. So we have 2 wind speeds and 2 wind directions, so that's a total of 4 in order to get the variance of the measurement of this traverse related to the uncertainty of the wind parameters. So then we change the wind speed to 8. We get a second value, which is 204 kilos per second. Then we go to 6 and we go to 195. We get a third measurement. And then we do the 4th. So for each traverse, we get 4 calculations in order to be able to show the uncertainty related to the uncertainty of wind measurements themselves. Now we've done 4 calculations for one traverse. So we're working on this traverse here, which was the 26th of August at 2 o'clock. Here's the 2 wind speeds, here's the 2 wind directions, and then here's the 4 fluxes that we calculated with the mobile DOAS software. So this is the 4 calculations we get to show the uncertainty related to winds. Then, once we have finished this, then I've created a separate spreadsheet where I'm looking at the daily properties. So not just an individual traverse, but for a day like this where we did 6 traverses, 5 of which were good and 1 of which we had to throw out. So on a day where we have 5 different traverses, then we also have the uncertainty with the repetition of the measurement. So the SO2 flux is not consistent over the day. It's in fact changing dramatically based on, so the past month and a half, the eruption has had very cyclical behavior where it's had big activity or very little activity, big activity, very little activity. And most of the gas emission is happening when there's big activity. So what the eruption is doing at the time we make the traverse has a big impact on how much flux we're measuring. So we need to take this into account when we're making the measurements, so that we're not only going out when the eruption is really strong and active, and we're not only going out at times when the eruption is very still and quiet. So in order to have some idea of the variance over the day, we have this is another spreadsheet where here we're in the tab for the summary of the traverses. So here on the 26th of August, you can see that we have 1, 2, 3, 4, 5 measurements that we're using. One that I marked in red because we're not using it. The reason we're not using this one in red is because when we started this traverse, we were already in the fringes of the plume. So we didn't have clear sky before we started. And so that gives us untrustworthy results. So we mark this one in red and we don't use it. Now we can see that, so for this day, see, I wrote a note, was in plume when started. It's very good to keep notes. One thing that I should have been taking notes on, and I didn't, is meteorological conditions. And I regret this. And I'm going to need to go back through all of my measurements and actually record what the weather conditions were at the time. So it's a very good idea to take those notes also. So now we're looking at another spreadsheet where we're looking at the daily patterns of the eruption. So on the 26th of August, we made 6 measurements, but we're only going to use 5 of them. So we have the minimum and the max for the traverse, and then we get the minimum per the day. So the minimum of these 5 measurements, and then the max per the day. Then we can go over to plot. Here you can see that for these are the daily range of SO2 flux measured by the traverse DOAS. This is in kilograms per second. And here you can see this is the daily ranges. So the minimum and the max for each day. So this was the 26th of August, the data that we were just looking at. And this is a really nice visual way to see the uncertainty that takes place over just the measurements that we make during one day. We measure the SO2 flux for a couple of different reasons. One of the reasons we focus on SO2 is because the main gases that come out of volcanoes are water, CO2, and SO2. And we have a lot of water and we have a lot of CO2 in the background atmosphere, but we have very little SO2 in the background atmosphere. So that means any SO2 above background is going to be easier to detect than water or CO2 above background. Another reason is that in the ultraviolet, we have instruments which are capable of measuring changes to the ultraviolet from SO2 in bands that don't interfere with the other common gases in the atmosphere. And a third reason is that SO2 itself is a gas that we're interested in. We're interested in SO2 because it is a pollutant. It affects people's health. It affects the environment. And so we're very interested in this. And so this specific instrument, the DOAS, the ultraviolet spectrometer that measures that we use to calculate the flux of SO2, we use this in many different ways, but one of the most important ways we use it is we use it to drive the SO2 dispersion model. So the amount of flux that we're calculating that comes out of the eruption at different phases or behaviors of the eruption are used to forecast how much SO2 is coming out of the eruption and how this is going to affect people on the surface. So how this is going to affect people in the downwind communities. So this is one of the primary reasons that we're interested in the flux. A secondary but also very important reason that we're interested in the SO2 flux is because the amount of SO2 that's emitted is very important for environmental reports, for knowing how much pollution is coming from each country. And it's important to know how the natural emissions from the eruption, for example, are affecting the measurements of the human-made pollution as well. A third reason is that because we're able to measure the SO2 flux, but we're not as easily able to measure the water flux or the CO2 flux, for example, or the fluxes of the halogens or the heavy metals. We're able to measure, we're able to take samples of the volcanic plume, and we're able to get the ratio of SO2 to other species, such as heavy metals or other pollutants that we're very concerned about, species that are in too small amounts for us to be able to measure their flux. But because we're able to get the ratio of these other species to the SO2, we're able to then scale the SO2 flux to how much is being emitted of these other pollutants. And this is very, very useful for us to know about how are the halogen gases affecting the waterways around Iceland, and how are the heavy metals affecting our water catchments, and questions like this. So the SO2 flux measurements have a lot of applications for health, and environmental reasons. So in summary, what we've shown you in this pair of videos is how to make measurements of SO2 in the atmosphere from a volcanic eruption using the Traverse DOAS technique, using the mobile DOAS software from the NOVAC Consortium. We've shown you how to process this data and how to process it in such a way that you're taking into account the uncertainties of the measurements due to uncertainties in meteorological parameters. And we've suggested best practices for how to organize the data and how to display it in a way that it can be useful for the community who is affected by the SO2 pollution. Thank you. If you'd like to learn more about the DOAS Traverse methodology, I recommend you check out the following resources.